Mercury. Mercury is an extreme place where direct sunlight drives daytime surface temperatures to about 420 to 430 degrees Celsius, while the thin, almost non-existent atmosphere allows night-side temperatures to plunge to roughly minus 170 to minus 180 degrees Celsius, all under a surface gravity that's only about 38% of Earth's. It's a common misconception that an unprotected person would instantly burn in daylight or immediately freeze at night. Because there is almost no air, heat cannot move by convection or conduction. A person would gain heat only by direct sunlight and lose it slowly by radiating heat to space. In the near vacuum, an unprotected human would not explode or instantly freeze, but would suffer rapid, life-threatening effects. The most immediate danger on Mercury is the sudden loss of pressure itself. Mercury's surface pressure is effectively a vacuum, far below the Armstrong limit, about 6.3 kilopascals, the point at which water can begin to boil at normal human body temperature. When pressure drops this low, ebullition occurs, meaning gas bubbles start forming in body tissues and exposed moisture, causing swelling and disrupting circulation. At the same time, oxygen can no longer be delivered to the brain, leading to hypoxia or oxygen deprivation, which typically causes loss of consciousness within about 10 to 15 seconds. If a person failed to exhale before exposure, the trapped air in the lungs would expand as pressure drops, potentially tearing delicate lung tissue in a condition known as pulmonary barotrauma. Blood remains liquid inside vessels due to tissue pressure, but widespread bubble formation, swelling, tissue damage, and circulatory collapse would rapidly follow unless the person were quickly repressurized and oxygenated. On top of these effects, Mercury's lack of atmosphere leaves its surface exposed to intense radiation and frequent micrometeoroid impacts, making survival without proper protection virtually impossible. Venus. Venus is an absolute hellscape. Its atmosphere is roughly 96.5% carbon dioxide, and the surface pressure is enormous, about 92 to 93 bar, which is roughly 92 times Earth's surface pressure, and comparable to the pressure encountered 900 meters below Earth's ocean surface. The atmosphere traps heat so effectively that surface temperatures sit in the mid-400s degrees Celsius, with a commonly cited value near 467 degrees Celsius, or about 873 degrees Fahrenheit. Thick, opaque clouds of sulfuric acid dominate the upper atmosphere and race around the planet at hundreds of kilometers per hour, while winds near the ground are slower but act through very dense air that still exerts powerful forces. An unprotected human would have no breathable oxygen and would be exposed to extremely dense carbon dioxide that rapidly overwhelms the lungs and prevents effective breathing. While the immense pressure would not crush the body outright, any rapid pressure changes could cause severe barotrauma to delicate tissues and lungs. At the same time, surface temperatures hot enough to melt lead would rapidly denature living tissue and destroy cellular structures, while the planet's chemically hostile environment adds further damage. The combined effects of suffocation, extreme heat, high pressure, and chemical stress make survival without specially engineered protection impossible, with death occurring very rapidly. Earth. Earth is the only known world to support life, but death remains inevitable. Our atmosphere, mostly nitrogen with about 20.95% oxygen, together with the planet's magnetic field, shields us from much of space's raw violence. The air burns up many small meteoroids, the atmosphere filters harmful ultraviolet radiation and helps keep temperatures moderate, and the magnetosphere deflects much of the solar wind. Still, Earth kills in many ordinary ways. Floods sweep people away, lightning strikes, wildfires race across the land. How a life ends depends on the cause. Some people slip away quietly, others lose consciousness suddenly from cardiac arrest or lack of oxygen, and some endure pain or distress, so final moments differ from person to person. By human standards, death on Earth is often intimate and familiar. A slowing heartbeat, a last breath of air, the sight of a sunset, or the distant roar of the ocean. For others, it will be very different, but those small, ordinary sensations are what make many goodbyes feel profoundly human. Mars. Mars's thin, cold air makes survival impossible without a pressurized suit. Its atmosphere is about 95% carbon dioxide, and surface pressure is only around 0.6% of Earth's, roughly 0.6 kilopascals or 6 millibars, far lower than even the summit of Everest. Average temperatures hover near minus 60 degrees Celsius and can drop below minus 100 degrees Celsius at night, although sun-facing slopes may briefly warm toward 20 degrees Celsius in bright midday. The sky is tinged red with dust, and winds can loft dust miles high during planet-wide storms. The biggest immediate threats are physiological. There is essentially no breathable oxygen, so hypoxia sets in rapidly, typically causing loss of consciousness within about 10 to 15 seconds without an independent oxygen supply. Because the air pressure on Mars is far below the Armstrong limit of about 6.3 kilopascals, a sudden suit failure would trigger ebulism, in which gas bubbles form in body tissues and exposed moisture begins to bubble, causing swelling and disrupting circulation. If the air in the lungs were not fully exhaled, rapid depressurization could also cause pulmonary barotrauma, a severe lung injury resulting from pressure expansion. Freezing would be a slower danger rather than an instant fate, since heat in Mars's thin atmosphere is lost mainly by radiation rather than rapid convection. In short, an unprotected person on Mars would almost certainly die quickly from severe hypoxia, decompression injuries, and cascading physiological failure. Jupiter. Jupiter has no solid surface. Below its colorful cloud tops, the gas gradually becomes dense fluid, then metallic hydrogen, and probably a deep core. Its atmosphere is mostly hydrogen and helium, organized into banded cloud decks of ammonia and other compounds, and its storms, including the Great Red Spot, are far larger than anything on Earth. Gravity near the cloud tops is about 2.5 times Earth's, which increases forces on anything that falls. The most immediate danger to an unprotected human is the intense radiation trapped in Jupiter's magnetosphere, which can deliver lethal doses in a short time without heavy shielding. If you entered the atmosphere, you would first encounter violent winds, frequent lightning, and chemically corrosive clouds. Continuing downward, crushing pressures and soaring temperatures would quickly destroy organs and denature tissue. Rather than instant vaporization, the body would suffer catastrophic mechanical compression, chemical breakdown, and thermal failure as it was pulled into the planet's deep, fluid interior. There is no gentle end there, only overwhelming physical and radiative destruction. Saturn. Saturn is a vast hydrogen-helium giant with no solid surface. Below its banded, honey-colored clouds, the gas gradually becomes denser fluid and ultimately metallic hydrogen surrounding a probable dense interior. The planet's average density is lower than water, about 0.69 grams per cubic centimeter, and spectacular rings of ice and rock encircle it while jet stream winds at the cloud tops reach extreme speeds, measured up to roughly 1,800 kilometers per hour. Gravity near the cloud tops is only slightly stronger than Earth's, around 1.06 to 1.07 times, so an initial fall would feel broadly familiar until there's nowhere to land. As you descend, pressure and temperature rise to values far beyond what biology can tolerate. Crushing stresses progressively compress tissues in any air-filled spaces, while rising heat denatures proteins and breaks down cells. Because high pressure raises boiling points, blood would not boil in the cinematic sense. Instead, the body would be catastrophically compressed, thermally and chemically degraded, and eventually assimilated into the planet's deep, fluid envelope. Upper layers are extremely cold, while deeper regions become intensely hot, so you would pass from freezing cloud tops into a furnace of pressure and heat, with violent winds and turbulent shear adding tearing forces. The combination of these hazards guarantees rapid, overwhelming destruction. Uranus. Uranus is a frigid ice giant with an upper atmosphere of hydrogen and helium and a few percent methane, which gives the planet its pale blue-green color. The planet is tipped nearly on its side with an axial tilt of about 98 degrees and lies far from the sun in dim light, while upper winds can reach several hundred kilometers per hour and up to roughly 900 kilometers per hour. Temperatures high in the atmosphere plunge to about minus 224 degrees Celsius, or roughly 49 Kelvin. An unprotected person would not freeze instantly on exposure because heat loss in that thin air is relatively slow. Instead, the faster threat is the complete lack of breathable oxygen. Severe hypoxia would typically cause loss of consciousness within about 10 to 15 seconds. Should you descend past the upper atmosphere, rising pressure and temperature would quickly exceed all biological limits, progressively compressing tissues in any air-filled spaces while intense heat denatures proteins and breaks down cells. There's no solid ground to stop the fall, and the body would ultimately be destroyed by a combination of suffocation, extreme pressure, and overwhelming thermal and chemical breakdown, as it is forced into the planet's dense, high-pressure interior. Neptune. Neptune is a distant cobalt blue giant whose upper atmosphere of hydrogen and helium, mixed with a few percent methane, gives the planet its deep color. Driven by these gases, supersonic winds lash the planet at speeds of 1,500 to 2,100 kilometers per hour, fueling dark, looping storms that churn through the dim sunlight. Temperatures high in the atmosphere are extremely low, around minus 200 degrees Celsius, and with depth, the visible clouds give way to ever higher pressures and warmer, denser fluid layers. An unprotected person would find the air immediately unbreathable and would lose consciousness from severe hypoxia within about 10 to 15 seconds, while the bitter cold and violent winds worsen exposure. If one kept descending, rising pressure and heat would progressively compress tissues and denature proteins, ultimately destroying the body within Neptune's deep interior. In short, death on Neptune would result from rapid suffocation near the cloud tops, followed by overwhelming thermal and mechanical destruction at depth. If you like this video, subscribe for more.